There's an argument running through every local AI space right now, and it has the shape of a sports rivalry. In one corner, llama.cpp, the engine that has carried this entire movement for 2 years, the thing most of us actually run every day. In the other, a newcomer written as a handful of small C files, 5 weeks old, tens of thousands of stars, claiming to open models measured in terabytes on machines with the memory of a mid-range laptop. The hype crowd says the newcomer makes graphics cards obsolete. The old guard says everything it does was already possible and the stars are a fashion. So, which is faster? I spent this morning reading both engines, the newcomer's source and documentation, and the specific files inside llama.cpp where this question actually lives. And I want to tell you 3 things up front. First, the question is malformed. Which is faster assumes they're running the same race. They are not. There are 2 different races hiding inside run a huge model from disk. And this is the part almost nobody in the argument has noticed. Each engine wins one of them. Once you see the 2 races, every confusing benchmark screenshot flying around this week snaps into focus, including the ones that seem to contradict each other. They don't contradict, they're timing different events. Second, buried in llama.cpp's source, I found the real reason this rivalry exists at all. And it isn't a missing capability, it's a default. A single default setting that on models bigger than your memory fails with an error that looks exactly like your computer is too small, when what you actually needed was one flag. I'll show you the precise lines where that flag lives, and the genuinely strange place you have to go to find it. There's a detail about the project's own benchmarking tool in there that made me laugh out loud. And third, the ending of this story is already written, and it's not a victory for either side. It's sitting in the llama.cpp pull request queue right now, with a title I'll read you verbatim, because it gives the whole game away. Standards note, and today it matters more than usual. I read code and publish documentation. I did not run these engines head-to-head. Every performance figure in this video is either a project's own published number, quoted as theirs, or a physical ceiling I calculate on air from disclosed quantities, labeled as arithmetic, where I couldn't verify something from my environment this morning. I'll say so out loud. Let's go. The 2 designs, 90 seconds of theater. Strip both engines to their philosophy, and you get 2 ways of staging a play. llama.cpp's default is, build the entire set before the curtain rises. Every backdrop, every prop, every costume for all 5 acts loaded, ranged, optimized, and then the performance starts. When the whole production fits in the theater, this is magnificent. Nothing ever interrupts a scene, and the crew has spent years making every scene change unnaturally fast. Colibri's design is, raise the curtain immediately, and let stagehands bring props per scene. A small permanent set stays on stage, and the project's own startup banner states the size with a confidence. I want to quote exactly, GLM 5.2 744B Mo int. 4 streaming CPU ready in 32 seconds, resident 9.9 gigabytes. 9.9 gigabytes on stage. For a 744 billion parameter production, curtain up in half a minute. Everything else lives in the warehouse behind the theater. Fetched when a scene calls for it, and the props used most often are kept standing in the wings. Why does the second approach work at all? Because of the single most important fact about modern giant models, stated plainly in Colibri's own README. A 744 billion parameter mixture of experts, model activates only about 40 billion parameters per token. Roughly 5% of the play is on stage in any scene. The other 95% is scenery for scenes you're not currently in. Neither philosophy is wrong. They're answers to different questions, and the 2 questions are the 2 races. Race 1, Decode, the drive race. The first race is generation, producing the answer, word by word, and here the arithmetic is beautiful, because it comes entirely from published numbers. 40 billion active parameters at 4 bits each is on the order of 20 gigabytes of weights touched per token. If every one of them had to come off the drive, a fast consumer NVMe drive reads a few gigabytes per second. Divide, and the cold worst-case answer is several seconds per word. Not because either engine is badly written, because that's how long the drive takes to deliver the bytes. We've run this exact division before on this channel. On the biggest model there is 17 gigabytes per word against a 12.78 gigabyte per second. Drive gave a hard physical ceiling of 0.75 words per second. And the engine we read was already achieving 84% of it. In race 1, the drive is the track, and no engine outruns its own track. So how does anyone claim usable speeds? Because race 1 has 2 regimes and the entire craft of a streaming engine is moving you from the first to the second. Regime 1 is the cold read, the scene calls for a prop that's in the warehouse. You pay the drive's price, full fare. Regime 2 is the warm wing. The prop was already fetched for an earlier scene and it's standing right there, you pay almost nothing. And here's what impressed me most in Colibri's source. It keeps its own books on exactly this. The code is full of planning and budgeting machinery. It works out before loading anything, what fits permanently in your memory and what has to be fetched, and it tracks and reports its own hit rate. how often the prop was already in the wings versus how often someone had to run to the warehouse. That number, which the engine states to your face, is the entire performance story of race 1. High hit rate, and you float above the drive. Low hit rate, and you are the drive. Their own dashboard shows what the best case looks like, and I'll quote it exactly. A 744B model at 4 tokens per second, TTFT 1.6 seconds, disk 0, on a machine large enough that the whole expert set eventually became resident. The warehouse trips stopped entirely, and a 744 billion parameter model ran at conversational speed with a first word in under 2 seconds. That's regime 2, fully achieved. On a small machine, the same engine, same model, honest readme. Expect a fraction of a token per second on a slow drive. Both numbers are true. The spread between them isn't the engine's quality, it's your hardware's position between the two regimes. Hold that thought, because llama.cpp is about to have its own version of both numbers are true. What I found in llama.cpp's source, the default, and where the escape hatch lives. Now the discovery, and I want to walk you to it the way I got there, because the path is the lesson. The old guard's argument is correct on paper. Llama.cpp has been able to read weights straight off the disk for years, using memory mapping, a mechanism the operating system has offered since before most of us were born. Map the file, and the system fetches pages on demand and quietly drops the ones you haven't touched. That is, streaming kernel edition. On paper, an oversized model should simply run slowly, not fail. And yet the weak screenshots show it failing, refusing enormous models outright with an out-of-memory error before generating anything. Both things can't be true, unless something in between is turning the streaming design back into a load everything design. There is, it's called repacking. Before running, llama.cpp by default takes the quantized weights and rewrites them into a layout your processor's vector units can chew through dramatically faster. On a model that fits in memory, this is pure win, and it's exactly the kind of hard-won optimization 2 years of maturity buys you. But follow the logic one more step, because this is the whole discovery. Repacked weights are new bytes. They are a transformation of the file, and the transformed version does not exist on disk. Memory mapping can only serve bytes that exist in a file. New bytes need real physical memory, all of them up front. So on a model far larger than your machine, the default pipeline stops being map and stream and becomes manufacture a rebuilt copy of most of the model in RAM, which, for a 160GB class model on an ordinary desktop, is arithmetic that ends in an allocation failure before the first token. And the error it produces reads to any normal person as your hardware is too small, when the truthful message would be your default is wrong for this size. The escape hatch exists. I read it this morning in the argument parser, the file common/arg.cpp, lines 2353 through 59, and I'll quote the definition. An option pair, repack, and ARS-NR. No repack described as whether to enable weight repacking, default enabled, 1 flag, turn repacking off, and the memory mapped path is back. The oversized model opens and runs at whatever speed the drive allows. The capability the newcomer is celebrated for, opening models bigger than your machine, has been sitting inside llama.cpp behind that flag. But here's the detail that turns this from trivia into a lesson. I went looking for where that flag is surfaced. You find it by reading the argument parser source. And then I checked the project's own benchmarking tool, llama-bench, the thing the community uses to produce all those comparison screenshots, and I searched its source for the no repack option. 0 occurrences. The benchmark tool cannot turn repacking off at all, which means every casual benchmark of an oversized model runs headfirst into the default, and the failure gets read as a verdict on the engine rather than on a setting. One more source detail because it completes the picture. Llama.cpp's memory mapping file also contains a prefetch path. When enabled, it asks the operating system to populate the entire mapping eagerly, the whole file, front to back. On a machine with a fraction of the model's size in memory, an eager full file walk means pages are falling out the back while the walk is still filling the front. The design assumption, load it all, then be fast forever, is visible right there in the flags. The code sets, it's a superb assumption for models that fit. It's the wrong opening move for models that don't. And that's the honest resolution of the capability argument. The newcomer didn't invent the ability, it inverted the default. Colibri treats not fitting as the normal case and plans for it before loading a byte. Llama.cpp treats fitting as the normal case and optimizes brilliantly for it. Defaults are policy. A capability hidden behind an undocumented flag, invisible to the project's own benchmark tool, is, for the person staring at an out-of-memory error, not meaningfully a capability at all. And I'd push that one step further, because it's the real lesson of this whole rivalry. For the median user, the default is the product. Most people will never pass a flag they don't know exists. Whatever happens out of the box is, functionally, what the software is, which reframes what the newcomer actually contributed. Not a mechanism, the operating system had the mechanism, the incumbent had the mechanism, but a stance. It made your model is bigger than your machine, the expected case instead of the failure case, and built the planning, the budgeting, and the honest bookkeeping that stance requires. A stance is also the cheapest thing in software to copy, no kernels to port, no years of tuning to replicate, which is exactly why the ending of this story looks the way it does. Hold that for 2 more sections. Race 2, Prefill, the batching race. Now the second race, the one the newcomers fans haven't priced in, because a conversation isn't just generating words. First, the engine has to read your prompt. The system message, the pasted code, the context. That phase is called prefill, and it is a completely different sport. Here's why. When generating tokens arrive one at a time, you can't compute word 10 before word 9 exists. Sequential by nature. But your prompt already exists, all of it at once, which unlocks the single most powerful trick in this entire field, batching. If 100 prompt tokens all need the same expert, you fetch that expert's weights once and push all 100 tokens through in a single path. The expensive thing, touching the weights, gets amortized across the whole batch. And this is where 2 years of maturity stops being abstract. llama.cpp's foundation is a library of hand-tuned computation kernels. Matrix routines specialized per instruction set, per backend, per shape, accumulated and optimized since this movement began. Deep batching over resident weights is precisely what that library is built to do. Feed it a long prompt and its prefill speed climbs with batch size, which is why heavy context work on it feels responsive out of all proportion to its generation speed. A per-scene streaming design sits at the opposite pole. Its defining move, fetch what this token needs, now, is exactly the move that resists deep batching. And I want to be scrupulously fair here, because the project is honest about it and evolving. Colibri's own README describes a batched forward path in its words, 2.2 to 2.8 tokens per forward when it pays. So batching exists there, it's real. And it's an order of magnitude shallower than what a mature kernel library extracts from a 100 token batch. Here's the law underneath, and it's the sentence I'd take from this whole video. A cache saves you the trip to the drive. Batching lets one trip serve many tokens. They are different savings, and the second one is where prompts live. Put the 2 races together, and the contradictory screenshots resolve. An engine can raise the curtain in seconds and win every short exchange decisively, and the other can spend its first minutes silently building the set, then chew through a 3,000 token prompt several times faster. First word versus long prompt. Startup versus throughput. Both results are true at the same time about the same 2 engines. Anyone posting one number and declaring a winner is timing one race and awarding both medals. The screenshot decoder, 5 questions that sort every benchmark. Before the buying advice, a tool you can keep, because this argument will run for months and the screenshots will keep coming. Anytime someone posts a number proving one of these engines, ask 5 questions of the image. If it can't answer them, it isn't evidence. It's a fan holding one stopwatch at one race. 1. Which race was timed? Time to first word, generation rate, or long prompt rate. Those are 3 different metals, and you now know an engine can hold one while losing another, truthfully, simultaneously. 2. What drive and what does it sustain? In the decode race, the drive is the track. A result without the drive's sequential read speed is a lap time without saying which circuit. 3. And this one is the trap we found in the source. Was repacking disabled? If the test used the project's own benchmark tool, you already know the answer, because that tool cannot disable it. An oversized model failing or crawling under the default setting is a measurement of the default, not the engine. 4. How long was the prompt? A 12-token toy prompt hides the batching race entirely. 3,000 tokens of real context reveals it. Any comparison using only one of those has quietly chosen its winner in the method. 5. Cold or warm. First run after a reboot, or 5th run with the cache full of hot experts. The streaming engine will happily tell you its own hit rate. A screenshot that omits it is omitting the single number that explains the result. 5 questions, and most of this week's viral comparisons answer one of them. That's not fraud, it's enthusiasm without a method, but it's why the 2 camps can both wave proof and both be sincere. Different stopwatches, different races, no lane markings. So which should you run? 4 honest cases. If your prompts are long, real context, pasted files, working documents, the batching race dominates your day, and the mature engine with the flag set correctly is the rational pick. The setup cost hurts once. The prefill speed pays on every message. If your pattern is short prompts and patience, overnight questions, batch jobs, the employee who works nights pattern we keep returning to, the streaming design's instant curtain and honest bookkeeping are exactly right, and generation speed is drive-bound in both engines anyway. Same track, same physics. If your machine is genuinely small, the 8 and 16 gigabyte laptops, the streaming engine's planner, which budgets before it loads and tells you its hit rate, is the difference between runs slowly, predictably, and an allocation error. Predictable slow beats mysterious dead. And if you're on a big box, memory approaching the model's working set, the races converge. The streamer's own dashboard shows disk 0 and conversational speed once everything goes resident, and llama.cpp is in its natural habitat. Up there, pick on ergonomics. Underneath all four, know your drive's sequential read speed. It is the single number that predicts your generation experience on either engine, and almost nobody who posts benchmarks states it. The ending is already in the pull request queue. Now the part that makes the Rivalry framing obsolete. I checked the llama.cpp pull request this morning from my own environment. One thread open right now carries this title, verbatim, Llama Stream Mo-e routed experts from disk. Read it again. The incumbent engine has an open pull request to adopt the challenger's defining idea. A second thread, closed after review, which is how open source thinks out loud, explored an adaptive scheme for caching CPU resident experts in graphics memory. There are further threads in the same family. Some wouldn't load from my environment this morning, so I'll characterize them only as linked below. But the direction needs no speculation. The ideas are merging, not competing. And it flows the other way too. The streaming side's README already advertises its young batched forward path. 5 weeks in, each project is reaching for the other's strength, which is the actual story of this whole field in miniature. We watched 3 independent codebases converge on trunk and stream earlier this year, and Colibri now ships 5 model families, 1 C file each, including a 975 billion parameter model I'd never seen claimed before. The convergence isn't slowing, the rivalry is a snapshot, the merge is the movie. So, standing watch on the record, the day that streaming pull request merges into llama.cpp, there will be a video here, same day. That merge would end the 2 races era and start something genuinely new. 1 engine, both defaults, chosen per model. It's the most consequential open thread in local AI right now, and it has a fraction of the attention the benchmark screenshots get. Honest limits 4, and today they're load-bearing. 1. I ran nothing. This video is source reading plus arithmetic. The performance figures quoted are the project's own published numbers, the banner, the dashboard line, the README's characterizations, and the ceilings are divisions I showed you. A rig test would add real information this video does not contain. 2. I could not independently pull one model's internal configuration. The per-layer expert counts for the newest family, so I deliberately built the Decode arithmetic on the 744 billion models published activation figure instead. Where I couldn't verify, I substituted what I could. 3. The pull requests are open, not merged. Open threads change, stall, and close. 2 of the 5 wouldn't even load for me this morning. Treat the merge as a direction, not a date. 4. Both projects move weekly. The flag's default, the batching depth, the family list, all of it can drift. The 2 races themselves are physics, and physics is the part of this video that won't age. Step back. The argument everyone's having is, which engine is better? And after a morning in both codebases, I think that's the least interesting question available. The interesting ones, which race does your workload actually run? Long prompts or long nights? What does your drive sustain? Because in race 1, that's the speed limit and the engine is just how close you get to it. And what do your tool's defaults silently assume about your hardware? Because the sharpest thing I learned today is that a 2-year-old engine contained the year's most hyped capability all along, behind a flag its own benchmark tool can't reach. Defaults are policy. Read the argument parser. So here's my question, and I'll pin it below, because it's the number that settles arguments and nobody posts it. Your engine, your drive's sequential read speed, and 2 measurements, generation tokens per second and long prompt tokens per second. All 4 together, or it's 1 race and half a story. A comment section full of 4 number reports would be worth more than every screenshot in this week's argument combined. Every link, both repositories, the exact argument parser lines, the memory mapping source, the streaming pull request and its siblings, and our earlier breakdowns of the trunk and stream family this all descends from is in the description. Read the flag definition yourself. It's 7 lines and it explains a week of internet. That's the standard here. Both sources actually read, the physics shown, the credit split the way the code splits it. If you'd rather own your tools than rent them, subscribe. That's what we do every single day. I'll see you in the next one.